Did you want to learn some chemistry today? I had heard you wanted to learn some chemistry. I had heard you wanted to learn about Graham's Law. Is it true? Is that true that you wanted to learn about Graham's Law? Well, that's excellent because you've come to the right place to learn about Graham's Law. You should have already read the little blurb, pages 472 to 474. 472, nope, that's 427. I like having dyslexia. 472 to 474 is the sections in the book on Graham's Law of effusion, or sometimes called Graham's Law of diffusion. Those two words are kind of similar, right? Diffusion and effusion. Diffusion is the random motions of particles that cause things to spread out from areas of high concentration to areas of low concentration. So you've seen that a bunch of times. Put food coloring into water, and there's a bunch of green right here, and there's not much green over here, so it randomly moves around and gets all over the place, right? I tend to think about this either, as marbles bouncing around. And so if you have a bunch of marbles here, eventually they're going to spread out everywhere. Or the way I prefer to picture it is like junior high kids, right? They're hyper. They move around like marbles do. So you put a bunch of junior high kids blindfolded. They can't intentionally go somewhere. So you have to blindfold them. And you put them in the cafeteria. So if you move them around, if you let them move around, they're going to spread out and take up the whole cafeteria eventually, right? That's diffusion. Effusion is then if you open a door. So if you open a door and they are blindfolded, they are not going to line up and all go out the door. But if they are randomly bouncing around, some of them will eventually accidentally go out that door, right? So I think when we picture what's going on when you pop a tire, right? Now not explode the tire, but like let's say you've got a car tire, right? That's my version of a car tire. Mrs. Higgins' students probably don't understand what a terrible artist I am, but my students are used to this, right? So let's say you pick up a nail, right? That's a nail. Right, so you pick up a nail in your tire, and there's an opening on the side. Sometimes you pick up a nail and it like seals around the nail. But let's say that there's a hole here. The gas particles are not trying to get out. They're not being forced to get out, but they move very fast. And since there's a spot they could hit and there's nothing there, if stuff's moving very fast, a bunch of them will go that direction. And since there's a high pressure inside the tire and low pressure outside the tire, you're going to get a net motion of stuff outside. So if I'm picturing those seventh graders and I put 200 of them and I give them all a bunch of pixie sticks, so they're all hopped up on sugar and they're all bouncing around all over the walls, and you open the front doors, if there's 200 junior high kids in the commons and there's like 5 outside the commons, well, you could get some of the ones outside coming in, but you're going to have a lot more of the inside ones going out, right? So Graham's Law of effusion or diffusion is basically about the motion of molecules. When we can compare their motions and how fast they're going compared to each other and that kind of stuff, right? So really we kind of look at it as rates. We don't focus a whole lot of things going through a tiny opening, but I think you should know when we're talking effusion, that's through a tiny opening. Diffusion is just random motions of particles. I have a nice little demo that I like to do in my class where we look at HCl and we look at NH3 and we open the lids on them and they bump into each other. And when they bump into each other, they form an ionic substance. And an ionic substance formed in a fluid, right? Gas is a fluid, makes solid particles, and it makes a smoke kind of thing. And it looks kind of cool. I've tried it like 4 times this morning. I can't get it visible on here. I tried it with the lights on, I tried it with the lights off. I tried it in a little tube. I tried it all over the place. You just can't see it. And a demo that you can't see very well on camera is not really worth 5 minutes of doing. So anyway, that's the idea of Graham's Law of effusion. It comes from the idea that at the same temperature, and if 2 gases are in the same place, they're going to have to be at the same temperature, they have the same kinetic energy. So if they're at the same temperature, they have the same kinetic energy. Kinetic energy equation is 1/2 mv squared. So if they have the same kinetic energy, we could just set those equal to each other. 1/2 mv squared equals 1/2 mv squared. Well, if I want to rearrange this a little bit, because this is not the final version of Graham's Law of effusion, but really it just comes from this idea. You don't need to be able to derive this, but I think it's helpful to see where it comes from, is I would just get rid of the halves, right? So then that's m1 v1 squared equals m2 v2 squared, right? Got rid of the halves, and I'm just going to label it. This gas 1 and gas 2. Then I'm going to rearrange it. So I'll divide both sides by m2. So I'll have m1 over m2 equals v2 squared over v1 squared. So see how it's flip-flop, right? The mass of gas 1 divided, and the velocity, this is not volume, this is velocity. Velocity of gas 1 is on bottom. But there's this squared factor, and over here they're not. So in Graham's law equation, we're going to go ahead and substitute molar mass for mass. So we're going to say molar mass of gas 1 divided by molar mass of gas 2, and I'm going to square root that so I can get rid of the squared over here, is going to equal, and instead of calling it velocity, he calls it rate of gas 2 divided by rate of gas 1. So the rate at which the gases move is a function of their molar masses, and it's an inverse square root thing. So the bigger a gas is, the slower it's going to go, right? Common sense-wise, I think that makes sense, right? If you have a great big gas, they're at the same energy, it's going to move slower. I think if we had quizzed you at the beginning, most of us would have gotten that right just from intuition, which is nice. Normally in chemistry, our intuition does not help us necessarily all that much, but here it does work out. All right, so the larger a gas is, the more dense it is, right? We saw that with our gas density thing. Density was a function of molar mass. Well, rate is also a function of molar mass. So if we see an example problem kind of thing, the other link I'll leave in here is SF6, sulfur hexafluoride. So if we wanted to say, well, how fast does sulfur hexafluoride move compared to nitrogen? Why do I care about nitrogen? Well, nitrogen is most of air, right? Air is 80% nitrogen. So when you're breathing out, when you're talking, your voice is the way that it is because of the size of your vocal cords and how tightly you're holding those vocal cords and the air that's passing by those. So when you breathe in helium, or if you breathe in sulfur hexafluoride, it's going to change the environment your vocal cords are in. So if we look at, if we did this to this problem and said, how fast does sulfur hexafluoride move compared to nitrogen? Well, we would say the molar mass of nitrogen compared to the molar mass of sulfur hexafluoride, if we square root that, that is going to be equal to the rate. Which one should go on top here? I have molar mass of nitrogen on top here, divided by the molar mass of sulfur hexafluoride. So if you look on the back of your periodic chart, you can find this equation if it's hard to read my awful handwriting. That's a flip-flop. So since sulfur hexafluoride's on bottom here, I'm going to say the rate of sulfur hexafluoride up here. I like to solve for things that are in the numerator on top. It just makes them a little easier to understand what you're looking at. So I set this one up like that. And the rate of nitrogen down here. Now, I'm not asking for the exact rate. Instead, I'm asking for a comparison rate. So you can just substitute in 1 for that, or 100 if you wanted to get a percent. So I'll put in molar masses. So molar mass of nitrogen is 28. Just using round numbers is good enough here. Divided by the molar mass of sulfur hexafluoride. Be good to pause me and figure that out for yourself. But sulfur hexafluoride 32 plus 19 times 6 gives us 146 grams per mole for our sulfur hexafluoride. It is much larger than nitrogen. Since it is much larger than nitrogen, remember nitrogen's N2, so it's 28, not 14. Since it's much larger than nitrogen, it's going to move quite a bit slower. Hopefully that makes sense. We know it's more dense. It can sink to the, it would sink in the room. It's actually dense enough that you can float things on it, like aluminum boats and stuff like that, like little aluminum foil boats, you can float on them and stuff. So 28 divided by 146, square root that. Whoa, what just happened? Oh, I did plus. See, Mr. Fred can't use a calculator. I did plus 146, and I'm like, 13 times as fast? That doesn't make any sense. So if you are estimating beforehand, if you're saying who should be faster here, and you get 13 times as fast, and I'm like, well, that doesn't work. It can't be 13 times as fast. Then you can realize that you don't know what you're doing. And instead of doing 13 times plus 146, you can do 28 divided by 146, and then square root that, and you get 0.436 to 1. So whatever rate nitrogen's going at, sulfur hexafluoride is going to go 0.436 times as fast, 0.436. So it's going 43% the speed of nitrogen, right? So it's a little less than half as fast, right? Nitrogen in the room moves at about 500 meters per second, right? So that means the sulfur hexafluoride is going to move at about 218 meters per second. That's pretty fast. Gas molecules actually move pretty quick. There is a difference between how fast they move and how fast they get places, though. So, side story, right? Earth science, you probably remember that the sun is 8 light minutes from Earth. It takes light 8 minutes to get from the sun to Earth. There's nothing that the light really interacts with between here and there. That does not mean that light is 8 minutes old. Light is actually quite a bit older than that because it gets formed in the center of the sun and then it travels an incredibly short distance, like nanometers, and is slammed into by something else, actually probably picometers. Right? It travels picometers, hits something else, stops, gets absorbed, re-emitted, travels like a picometer again, gets absorbed, re-emitted, travels these very, very, very short distances over and over and over again at the speed of light. But because it keeps stopping, it doesn't travel very quickly, and so it doesn't get to the surface for like millions of years. So if you have something generate a smell, hopefully it's a pleasant smell and not a, bad kind of smell. But let's say somebody generates a pleasant smell on one side of the room. You can't expect to get on the other side of the room in even a few seconds, even though light travels really fast, even though the molecules are traveling at 100 meters per second, because they travel at 100 meters per second, hit something, bounce backwards a little bit, and then go and then hit something, right? And so they're going back and forth, but they, you can still, it'll still travel across the room, but it doesn't travel across the room as fast as the molecules themselves are moving, if that makes sense, right? So Graham's law of diffusion, the main ideas there, right? They are at the same kinetic energy at the same temperature. So the heavier a gas is, the slower that gas is going to move. Today's quiz will just kind of be over those ideas. Then watch the sulfur hexafluoride video. That's just entertaining. That's just fun. I don't buy it because it's really, really expensive. It's like $300 for a lecture bottle of it. But it's pretty cool to see. And then tomorrow we'll work more problems with it, give you basically the 3 types of problems. We can solve for like how heavy is a gas, solve them for a molar mass. We can solve for how fast does a gas move, or we can do this third type of problem, kind of like I did today. How fast does this gas move compared to this other gas? Anyway, hope things are going well for you. Stay safe. Keep your chin up. I know nobody's prefers school like this, but maybe you do because you don't have to see me for as long. 11 minutes is less than 42 minutes, right?